I'm lecturer today in the community in our department. Professor Krishna. He's no stranger to the department or the institute. He has been coming here almost every year or once in 2 years. That's bad. You are actually
92, yeah.
He spent a sabbatical here way back in 1992 when some of you were not even born. So, and he's currently the ETC Chair Professor of Systems Engineering, and he has been Chair Professor. He's also the Board of Trustees Distinguished Professor at the University of Connecticut. He's made some fantastic contributions covering the areas of, essentially the broad area of decision making in complex systems. And the type of mathematical paraphernalia that he has used in his work sweeps the entire spectrum, all the way from stochastic processes, neural networks, dynamic programming, optimization, data theory, you name it, he has actually used all the mathematical paraphernalia. Some extremely rigorous results he has. And so it's good fortune that he's here today. Let's listen to him today on ABR Streaming of CBR and VBR-encoded videos, a topic that he picked up only 2 years back. And so another distinguishing characteristic of Professor Krishna is that they've been changing areas. That's because of the fantastic mathematical expertise that he has. So let's welcome Professor Krishna and his wife.
Thanks. Okay, this particular area is replete with all these acronyms. So ABR basically stands for Adaptive Bitrate Streaming. Adaptive bitrate is the ABR. CBR and VBR are different ways of encoding videos to compress raw video into something that you watch on your cell phones or iPads. So CBR stands for constant bitrate. VBR stands for variable bitrate coding. I will briefly explain those. So the streaming idea has been there almost since 1920. So the music that you hear in elevators is essentially streaming. And with iPhones and iPads, this ABR is a very interesting decentralized way of doing the control of streaming videos. Is being done on the client side. So that's where all the adaptation logic is. And it's a very clever way of basically watching videos with good quality. So these are a couple of publications that we had. I got into this area, maybe let me just go back a little bit, because of Professor Bing Wang. Bing is a student of Dawn Tousley from UMass. She's a full professor in computer science and engineering department. And Yan Won Quen is her PhD student. And also, I know a little bit about Brother Sen. He used to be senior to Bing Wang. I never met him. In fact, I don't know any of the other people, but we collaborated and got these 3 different papers. And one of them was actually Best Paper Award recently. So the reason I got involved in this is Bing came to me about 2 years back and said, hey, some Italian guys have come up with this PIDs for ABR video streaming. And the guys from CMU have this so-called MPC, this is a model predictive control and robust model predictive control, and they're claiming that PID doesn't work. At that time, I happened to be working with Carl Astrom from Lund, because we were developing some foundations of control for thermal fluid systems. It's basically HVAC type systems for UTC. And he came and gave 2 lectures in my course on PID, and he taught me how to tune these PID controllers. I said, hey, that can't be. And one of the things that I learned from him is that 95% of the controllers that people use are PIDs. although these MPC guys have been jumping up and down for the last 30 years, it has maybe made a dent of like 2 to 3% in the actual real physical world. And that's because PIDs you can tune very easily. And our experience has been that PIDs actually do a lot better than MPC and robust MPC. They're about maybe 200 times faster, and they do better across the entire spectrum of quality of experience. So that's one positive thing for age-old PID controllers from the 1940s and 50s. So it turns out that you can use them for both constant bitrate as well as variable bitrate encoding. So constant bitrate basically means that whether the scene is complex or simple, you use essentially the same bitrate for encoding. So for example, if it is like credits text, you use essentially the same number of bits as well as to represent complex scenes with motion. Whereas a variable bitrate encoding uses a different number of bits to encode different things. For static things, you use small number of bits. For things with complex motion and a lot more fighting and songs and things like that, you might use more number of bits. So the thing is, you can make the PID with some machine learning type of, basically essentially regularized least squares to actually work for both the CBR and the VBR, and also using some preview control type of strategies. So another thing that is very important is people really don't have too much data that they can use per month, say 2.5 gigabits they can use per month. Whereas if you want to watch some Netflix type of things in HD, that might take you like almost 3 gigabits per second type of video if you want to watch it raw. So can you reduce the data usage? And it turns out that you can make PIDs things work for reducing the data usage also. So video streaming is ubiquitous. In fact, 82% of the internet traffic will be video by 2021. And there are lots of providers. So what is the difference between video streaming and video downloading? Video downloading, you basically download the entire movie and then watch. So there's no buffering, nothing. But it will take you a significant amount of time before you can start watching. Whereas video streaming basically means that you download the first chunk and then start watching immediately. So there's less time that you need to wait to watch your video. So the streaming is extremely important nowadays. However, the streaming experience could be better. I'm sure you have seen this kind of things. In fact, it was very painful for me recently when I went from Connecticut to Pittsburgh, and I had to go through some roads very close to Penn State, and horrible reception. So I was always getting this kind of reception. So too many buffering events. So the question is, you can actually make ABR work in those kind of situations by, you really know where you're going, so you can actually have a GPS-aided adaptive bitrate streaming. The quality could be low video bitrate. That's another major problem. And also, if you start changing your bit rates too much, your quality of experience is going to be really bad. That's like having your controller changing all the time. So you would like to minimize the bit rate changes. So those are the three major things. And of course, you also want to not use too much of your data from your data plan. And also, the network bandwidth is estimated could be in serious error. So one of the problems with all these MPC and robust MPC type of things is that they're very sensitive to estimations of the network bandwidth. And that has actually been proven again and again, and people don't learn those lessons. In 1970s, people claimed that, oh, we have these LQ controllers, we can go and do fly-by-wire with F-8 aircraft for NASA, and they became essentially unusable, very bad controllers. And that's where all this robust control type ideas came up, whereas the old PID controllers used to work pretty good. So adaptive bitrate streaming is a way of realizing that you know what the network bandwidth is that you can do at the client side or the user side. And also you know what the capabilities of your iPad and iPhones are. The capacities of your CPUs is known. So you can use this ABR to improve the quality of experience. So let's try and see what happens in video streaming. So your raw video is basically represented in terms of three things. One is the frame rate. So it depends upon whether it's PAL or NTSC. So for NTSC is like a 30 frames per second. For PAL is 24, 25 frames per second. So I would say 30 frames per second. The frame size is basically how many pixels you have. So which is like, nowadays it's very common to have 1920 by 1080 as the 16 by 9. Now it is also like a 4K, now 8K and 12K even is the frame size that people use. And also the depth is the number of colors that you'll have. If it is 256 colors, you'll have about 8 bits. 16 bits will be 65,536 different color combinations. And there are some with even 32 bits also. So if you use, say, 16 bits, 2K, which is 1920 by 1080, 30 frames, you're talking about 1 gigabits per second, okay? So raw video, you're not going to watch on your iPhone. So what is typically done is you encode this video in different streams. They're also called different tracks, different renderings or different representations. And typically Hulu and YouTube use as many as 5 or 6 of these different tracks. So the same video is encoded with higher bit rate or medium bit rate or the lowest bit rate. So 5 or 6 different combinations you'll have. So essentially the same video in different qualities. And depending upon the network bandwidth, which you can measure at the iPhone, you can select the different segments. So these are basically segmented into chunks. They're called chunks, or segments. So you select different segments and then put them together as the video that you're going to play on your client. So here, for example, you selected the one from the second track, from the first track, and then the third track, and then put them together and render in your client. So this whole rate adaptation logic is being done in your iPhone. So that's why it's highly scalable approach for this. And this was actually initially started by a company called Move in 2006, which actually went out of business, but now it's become a very popular technique for streaming. So what are the challenges in ABR streaming? As we mentioned, first you need to balance these three conflicting requirements. You want to maximize the quality. Basically, you want to have as many of the high tracks, minimize the quality changes. It's basically flipping among different bit rates is not good. That's basically changing your control signals. And you want to minimize the buffering events. That means you don't want this thing to basically become empty, the buffer. So you don't want it to go to 0. And typically this buffer is measured in terms of the number of seconds of video that you can play, right? That's the buffer. So you want to do this in the presence of high uncertainty. So your bandwidth could be varying like as shown, it's a stochastic quantity. And the bitrate of the video content can be highly variable. So as we mentioned, the CBR video, you essentially have each track has nearly constant bit rate, whereas VBR video, you can have highly variable bit rate for the different tracks. Okay, so we should be able to work with both CBR and VBR video. VBR is a lot more popular nowadays because you can have high quality representations of your video. So another thing that you also want to have is reduce the data usage, and you want to be insensitive to estimations of your bandwidth. So typically the bandwidth is estimated maybe based on the last 20 seconds, what the bandwidth was, and use that to predict what the bandwidth is going to be into the future. So typically 5 chunks is what people use. And a chunk size varies anywhere from 2 to 8 seconds. So what I want to do is talk about 3 things. The first paper is on ABR streaming for CBR encodings. This is the first time we actually showed that the PID actually works better than the existing schemes, and then how we extend it to the VBR. So VBR, you need to be a little more careful. You need to have different ways of looking at the problem in terms of giving differential preference to the different segments, so on different chunks, and also have this preview because you will know exactly how your video is going to be over the future through something called the manifest. So you could use that information to actually set your buffer sizes. So there's an outer loop control that you could use to set your buffer sizes. And then you can have something called quality aware strategies where you try and maximize your quality for a given data plan. And then where we are going in the future. So you may have known how this cruise control in a car works, whether it's a manual or a cruise control. But yeah, anybody that uses an iPhone or iPads, anything. So it doesn't matter who. So it has been used both Android phones or the iPhones and iPads. Yeah. So we've actually implemented something called Dash, dynamic adaptive streaming with HTTP. It's basically what it is using is the HTTP protocol, like basically rendering your video as web pages. So that's why it's very popular now. Okay. So if you have, so this is a regular feedback control loop. You have a card dynamics with actual speed and the target speed that you set in your cruise control. And then the throttle controller takes the error between the actual speed and the target speed, and that error goes through a throttle controller to give you the control signal. The same thing happens in ABR. Here we have got a buffer level, typically in terms of the number of seconds of video that you're going to have in the buffer. And there's a video player dynamics. It's essentially very simple first order dynamics for this. Is basically the filling rate minus what you're using. And your adaptation logic uses the target buffer from the buffer level. And that adaptation logic is what we are saying is PID with some enhancements. So what is a PID controller? It takes the error and constructs that control signal as proportional to the error, and then the integral of the error, and also the derivative term. So it turns out that in our controller, all we have to do is only the first two terms, the proportional and the integral. And the derivative could be quite useful for the VBR, although we never had to use that. We have a different way of handling the VBR. So this TD is what is known as the planning horizon for the derivative part. And this is a very good way of illustrating what the PID does. So if this is the error signal, so what PID is doing is taking the current error, that's my present, that's Kp times EFT, and then the integral of the error multiplied by the integral gain, and the derivative times the det by dt, there's the slope times the kd. And in fact, this TD can be thought of as the ratio of KD by KP, which is the horizon that you're looking at. Okay? So PID basically predicts by linear interpolation of this error signal. And derivative time is this prediction horizon. And in order to make it work, you need to do quite a few interesting tuning things. One is something called the set point weighting, which is to make sure that you don't suddenly have a very bad transients initially. That's the set point weighting. I'll briefly explain that. Especially when you have a noisy type data, you may want to do filtering. And something called the wind up is when you get into saturation. In our case, it's going to be when my control signal becomes less than 0. I want to basically set it back to some positive epsilon so that I get the highest bit rate. So wind up protection is another thing that we'll be using. So there's lots of interesting things that people have done over the years to make these PIDs work. So how does the PID work in our context? So you start with the current buffer level. So you get your error signal. There's a core controller that gives me a control signal. And then these enhancements are going to be to take care of the errors in my estimated network bandwidth, and also looking ahead into the future, especially for the VBR. And also we'll figure out a way of also changing my buffer level depending upon what is going to happen into the future. This is going to be a preview controller associated with this XR. And the bit rates that you're going to use are going to be quantized. So this U of T may be a continuous signal, but the actual bit rates that you're going to download are going to be one of those 5 or 6 different track levels. So it's going to be quantized bit rates. So this is where we will be using some regularized least squares to determine what these RT stars are. Yeah. Right.
So in some sense, you want to discourage rebuffing events. But there might be trade-offs where I think rebuffing events as opposed to component volume. How
Yeah.
that captures this?
Yeah, all that stuff is being captured in this enhancements. I'll indicate what are the changes that we do. So the first term that is going to be is try to match this U of T as close as possible. It turns out to be the way that we formulate it. We could have formulated it as a stochastic dynamic programming type of problem, but we have a very nice way of, maybe that's a clever thing that we did, is to make the dynamics between XT and UT to be linear. And so there's going to be a least squares that's associated with that. Plus, there's going to be an extra term that we add to our least squares that discourages sudden changes. Okay, so you will have lambda RT minus 1 squared. That's sort of like a regularization term that takes care of the quality changes. So the buffer thing is being handled here. The quality changes is being handled in this thing. And it turns out that unlike MPC and robust MPC, and there's something called Panda, which is probe and adapt with consistent quality, this is insensitive to errors in this bandwidth estimation by as much as 50% or so. So it's very stable and very robust to uncertainties in the CT. It's a good question. So what are the buffer dynamics? So this is a mildly nonlinear system in the following sense. So when you first start out, it's going to take some time to download your initial video, right? So let's say that there's my startup delay. There's going to be startup latencies like delta seconds. And it's also quite insensitive to this delta also. So this is what is known as the fill-up rate. So CT is the offered network bandwidth. RT is the rate at which you're downloading. Okay, so the CT by RT is the fill-in rate. And once you fill up your first initial buffer, you can start playing. So the future things are going to be my fill-in rate minus the thing that I'm using. And of course, I can only use if my buffer is more than this delta, which is the chunk size. If I have only a chunk, then I can start playing things. Okay, so this is where there are some nonlinearities comes in. So XT is basically the current buffer level. This is going to be in seconds because this is a dimensionless quantity. So XT is going to be in seconds. CT is the bandwidth in some units, some bits per second. And delta is the chunk size, which is going to be in seconds. Startup latency is also in seconds. And the bitrate selection is going to be in the same units of the CT. Okay? So it's a very simple dynamics. So I was very surprised that given this simple dynamics, why the heck PID is not working? So I knew immediately as soon as she came and told me that, yeah, the computer science people don't know how to tune controllers. So if you select your thing, if you remember, this is how I define CT by RT as my control signal. If I just use my UT to be CT by UT, it won't work. Okay? Because you're basically dividing by UT, which could be a nice control signal, but C is a stochastic quantity. So that's where you need to have some preview of things. So my control policy is going to be like this: UT equal to KP times error, KI times the integral. What I'm going to do is add back my 1 of XT minus delta to my control signal all the time. And what that does is it makes the system linear. If I go and compute my closed loop transfer function, it's going to be XS by XR of S, which is simply going to be this second order system. And this system has got some really interesting properties. So if you are control guy, an undergrad control, you will know that this is a second order system. And for the second order system, you like to have nice damping ratio. And another interesting thing is this is what is known as a type 2 system. So what it means is that if I apply a ramp input to this, or even a step input, what is that the DC gain of the system? That means when S equal to 0, the DC gain is 1. That means I can track step inputs exactly. In fact, I can track the ramp inputs also exactly using this strategy. Because if I apply a ramp input, let's say like 1 over S squared, and if I do partial fraction expansion, there won't be an S term. That means it can track ramp inputs with 0 error. So it's a type 2 system. So it's very interesting. And it's a linear system, that means it's easy to control and analyze. I will know how to pick my damping ratio. If I know how to pick my natural frequency, I can make the system the way it should behave as far as U to T is concerned. But my control signal is not U, but is R. So how do I do that? Well, that's why our first enhancement is to solve a moving horizon regularized least squares. So if CT by RT is my U, let me try and solve this problem. UK RT minus C hat K, where UK is my signal over the next window of length L from the current time. And I'm going to use a constant signal over this length L. And typically L is like 5 chunks. This is sort of like MPC. You're looking at 5 steps ahead to determine what my control signal is going to be. So one of the assumptions that we're making is that, hey, my control signal is going to be constant over a length of L. And since R is a quantized signal, all I need to do is search over 5 or 6 numbers, whatever the number of tracks that we have, to find out what this solution is. And to address your quality changes thing, this is the extra penalty term that I'm using, RT minus 1. So this number I will know, and this is the one that I want to compute. Okay? So that's also at least one of the problems. Now let's go and take a look at what happens is that this extreme bit ranges basically get reduced like this. So I'm addressing the quality aspect using that regularized term. Okay, what do we do with the initial ramp up? So this is where the set point weighting comes in. So if XR is much greater than XT, that means if the error signal is very large, like initial startup, suppose my buffer size is 60 seconds, my initial thing is 0, this error signal is going to be very large, that means my U is going to be large, that means I'm actually going to use low bit rate. So it tends to go very slow. So people have already looked at this kind of stuff in PID. What is done is that instead of changing your XR suddenly from 0 to 60, you can make it a beta times XR. So this beta is what is called a set point weighting. Or you could have also done a slow increase of XR. Since mine is a type 2 system, I could actually track things very well. So there are lots of different ways of doing this thing. So we chose, this is one realization of that, where is I'm going to multiply this by some beta times XR. In the PID control literature, what this is a so-called 2 degree of freedom PID, because this actually gives you extra zeros in the numerator, and that actually helps in the performance of the system. So that's called the set point weighting. So instead of asking for XR minus XT, now we're going to ask for beta XR minus XT. Beta is a number between 0 and 1. So the one that we use is like 0.2. My control signal goes down, therefore my RT goes up, and my bit rate is going to be, again, because of the regularized least squares, is going to have small changes. So another enhancement that we make is that what if the bit buffer level is more than the target buffer? That means my UT starts going down, and I tend to use lowest bit rate when the UT goes down. So what I do is that we don't let UT go down, become less than 0, because it's a ratio of positive numbers. So actually there's a constraint that my control signal should be non-negative. So we stop it when UT is a small quantity, in which case we start using the highest bit rate. And that sort of makes sense from a regularized least squares, because UT RT minus CT squared, so RT has to go up as long as you maintain your UT to be greater than 0. So that's what is called the anti-wind-up. That means the control signal is getting saturated. So the way to handle that in the PID context is basically don't do the integration. So the skip integration when you get into this kind of situation. That means you use a proportional controller for the region when UT is pretty close to 0. Another improving startup performance that we do is we make our KP and beta to be time varying for the initial maybe 120 seconds or something like that. So the reason why we do that is we want to have a fast pickup. That's one of the things that we had observed with MPC is that it can pick up things very fast initially. And this is the way to handle the thing by making KP to be basically come to its steady state value by following a first order dynamics. So all essentially we're doing is sort of like a filtering our control signal using this scheme. And this is the new addition that we have done for our journal paper after our conference paper. So this is our final controller. So we have adaptive set point weighting, that's the beta thing, and adaptive PIA Core Controller, where we're adapting our KP, and there's an anti-wind-up thing when UT is small, and moving horizon regularized least squares, that is quite insensitive to the estimated network bandwidth, and then do the stuff. So how does this scheme work? So we evaluated with about 50 LTE network bandwidth traces. Those are the box plots of the different traces. You can see that there's a wide variation in the bandwidth, the throughput. And there were 3 video bit rates sets. That means the number of tracks, 5, 6, and 7. And the videos were like 15 minutes. It's a constant show. Network bandwidth was predicted over 20 seconds. So if you happen to have like chunk size of 4 seconds, that means we're looking at like five steps ahead, 5 steps backward to estimate our network bandwidth. And the way we do that is using the harmonic mean over the last 20 seconds. That people have found is quite insensitive. Very good estimate. So the QoE metrics that we're using, average bitrate changes, and rebuffering. And the algorithm that we compared is the BBA. BBA is basically buffer-based algorithm. It turns out that this BBA is nothing but proportional controller. Okay, so BBA can be interpreted as part of our PID controller. And MPC is the one that from CMU. And these are the 3 metrics that we answer is, hey, how does it perform? What is the overhead? And how do you select the parameters? So in terms of the overhead, we find that MPC is about 200 times slower. So what it means is it takes about 4% of your computation time for a 15-minute video. That's like 36 seconds, whereas ours takes like 0.4 seconds. So we basically spend like 99.8% of the time on the actual streaming, whereas these guys spend about maybe 96% of the time. So that's significant. So first finding is that without the dynamic KP and beta, so what if we didn't do that journal paper version? So we find that average bit rate is basically following the MPC quite well. But in terms of the average bit rate changes, it is significantly better than MPC. So the red one is, so more towards the left side is better. And look at the total rebuffering, about almost like 68%, 85% lower rebuffering time. So significant performance improvements in the quality of experience and very little in terms of the average bit error rate compared to the MPC. Okay, what about the enhanced version? Enhanced version is about 15% to 30% higher average bit rate compared to the PIA and BBA, only 5% lower than MPC for the first 2 minutes, 20% lower rebuffering than MPC, and 50% lower in terms of the average bit rate changes. So in terms of the quality of experience, this is a lot better than the existing algorithms. Another thing is, in terms of the computation time, BBA, of course, is the fastest. We are only about twice as costly in terms of the computation time. where the MPC is about 200 times slower. Okay, how do we find these parameters? So we did some really interesting experiment here. You can actually evaluate how good the quality of experience is using a metric that CMU guys had developed. We use exactly the same thing. And then vary all sorts of parameters. So what are the parameters that we have? The startup delays, the chunk size, the number of tracks, and network bandwidth, right? So we vary across all the different 50 traces, and then see the KPKI parameters that come within 90% of the best quality. So that's how we came up with this heat map. And you can see that in this range of KP and KI, it works extremely well across all the different 50 traces. So we actually find a point in this range that works the best for all the 50 traces, and we keep those as constant things. So you can have a constant PIA controller that works across any kind of video signals. So that's basically for the CBR. That was a very good thing where we actually showed that the PID can work as well as or better than the existing schemes. Now we wanted to go and see how does it work for the VBR signals. So VBR encoding. So in VBR, what you do is for different parts of the video, you're going to use different bit rates. And that is actually now it is becoming very standard, except for AT&T, which still uses the CBR. About 10 out of 12 providers, I think, use the VBR encoding. There's two versions of it, H264 and 265. 265 is supposed to be 30% better than 264. So all you're doing is allocating more bits to complex scenes and less to the simple ones. And it is better quality to bits ratio compared to CBR. They often treat VBR and CBR the same. So you use peak track bit rate. And it leads to actually, very interestingly, the complex scenes actually have lower quality than the simple scenes. That's what happens when you actually use the existing ones. So what if I just plug in the actual chunk sizes in the existing ABR schemes? This is not a good idea. That's why you need to have a different enhancement scheme for VBR. So typically what happens in VBR is that you set the peak for each track, and then you code depending upon the complexity of the scene, okay? So typically, this is going to be the peak for maybe the fifth guy, the fourth guy, third guy, and so on and so forth. All right, so one of the things that we did was, what is the difference between the CBR and the VBR? So we analyzed lots of different videos encoded by YouTube, and FFmpeg is an open source way of encoding videos in H264 and 265. And what we wanted is understand what exactly is going on with VBR videos. What is the difference between VBR and CBR? And can we come up with some principles for designing adaptation logic for VBR? So one of the first things that we did was we evaluated the raw video quality. Raw video quality can be evaluated using this so-called spatial information, the temporal information of a video segment. And we divided the video into simple chunks. So depending upon the quarter they're in, quarter 1, quarter 2, quarter 3, quarter 4 chunks. So different quartiles. And one of the things that we find consistently is that the quartile 4 chunks have high spatial and the temporal information. So what it basically means is that the scene complexity is proportional to the chunk size. So chunk size can be used as a metric which is known, so it's very easy to implement in your client, which is basically your iPhones, because you will know what the chunk size is that comes from the meta file. And consistently, depending on whether you do it in H264 or 265, the Q4 seems to be a measure of the complexity. So you can actually use the chunk size as a measure of the complexity of the scene. So can we use that information? So complex scenes, actually when you go and implement existing ABR schemes, actually the Q4 chunks get lower quality. Is it in the encoding scheme or is it in the ABR scheme? We can only fix the ABR part of it. So good adaptation, good ABR should be scene complexity aware. So as we showed that the relative chunk size can be used for this scene complexity. So the principles that we came up with for VBR, basically we just needed to add an extra outer loop controller for this, and also a non-myopic controller. That means you consider not only the bitrate of the immediate next chunk, but also the bitrate of multiple future chunks. So typically we look ahead like 5 chunks or next 40 seconds. So if it's going to be a 2-second chunk size, next 20 chunks, if it's going to be 8 seconds, you just look at 5 chunks. And one of the things, since we don't know where the problem is, whether it is in the coding, the Q4 chunks, although they're supposed to be complex scenes, actually they were getting lesser quality. So how do you measure the quality? There are basically 3 different ways of doing it. One is something called the peak signal to noise ratio, which can be measured. And also something called the VMAF, that's very common. VMAF stands for Video Multi-Method Assessment Fusion. And what we find for Q4 chunks is that there's a huge variability in the quality of the encoded videos. So can we, for example, since Q4 chunks are supposed to have higher quality, and they're not, so can we give preferential importance to Q4 chunks? And it's quite easy to do in our least squares. Basically, increase either your UT, decrease your UT, or increase your assumed bandwidth. So there's a factor that we add to give preferential treatment to the Q4 chunks. Another more interesting thing is, since you know that you're going to have chunks of maybe higher quality Q4 type chunks coming up, you can actually use the preview to set your buffer level. So make the buffer level, the target buffer level, dynamic depending upon what you're going to observe in the future. So this we basically look at like somewhere around 200 seconds into the future to set our buffer sizes. That is basically like a supervisory controller that we use. Now we can actually extend it further into have another layer of control when you're driving on a road. So if you know that you're going to go from, say, Boston to Pittsburgh, and you know you're going to experience mountains, you can actually pre-plan and have your buffer level set. Basically download all your video so that in the places where you don't have signals, you can actually be playing from the buffer. Okay, so you can really do some really nice, intelligent, multi-level controllers that people have worked with in the control theory. So the non-myopic and differential treatment is the following thing. So suppose these are the chunk sizes over the next n chunks. And this is, suppose, my network bandwidth. So what if I try to be greedy? Basically, for this one, I'm going to use the maximum thing. And for this one, I need to have actually higher selection of the rate. But actually, I can only do this much because I used up the things here. It is like basically spending your money as you get in here rather than saving it. So you could actually have a bad quality for this particular chunk if you just use this kind of strategy. On the other hand, if you plan like this, where you're going to use less here and more here and so on and so forth, you can basically get a better selection. So that's what we try to do in our enhancement to this VBR. The second thing that you can also do is you can actually plan for your buffer level by using this kind of strategy. Suppose this is my network profile, and this is what I'm going to have in the future in terms of the chunk size. And suppose that this is the track that I'm playing. And if I were to select my things at this level, at this time, it's too late. So essentially my buffer level basically goes to 0, and I'll have buffering events. Whereas if I plan earlier and reduce my track to the lower level, I won't have this buffering problem. Okay? So those are the three principles that I have: non-myopic, differential treatment of high quality, that's the Q4 chunks, and also looking ahead for my outer loop controller. So now we have this PID feedback controller, the same one that we used to have. This optimizer now has this short-term statistical filter that raises up in the optimizer to select RT that's going to have a higher RT for Q4 chunks. And also you have with the long-term statistical filter that's like looking at like maybe 200 seconds to look at how to set my buffer levels. Okay? So if you're going to have your mean that's going to be, your RT is going to be a lot higher than the mean, you're going to rise up your XRT so that you plan for the future. So that's basically what we call the proactive controller. So this is what our principle is. So this is my actual bandwidth, and this is my short-term average of the chunk sizes. Basically what you're doing is filtering in the context of PID. And what you're going to do is for the ones that are Q4 chunks, you're going to inflate your available bandwidth, and you can do that using this factor alpha t. So alpha t is the bandwidth scale factor, which is going to be greater than 1 for Q4 chunks and about like 1.1 for 0.8 or so for the Q1 through Q3 chunks. And by just changing this, and this is basically again a regularization term, which is in terms of the average bit rate of the tracks. And this is going to be, if you're going to be using the same track, you're going to have this term. If you're going to move to a different track, you won't have this extra term. Okay? So by just basically changing this objective function with this factor alpha t, you can actually make the quality of Q4 chunks a lot better. So how about my buffer level? So this target buffer level used to be a constant. If we know that you're going to have large chunks ahead, you're going to increase it. And that's there in the paper how we do that. It's quite easy to do. So here we use the 200 LTE network traces. And our metrics were how well we are handling the complex scenes, and what percentage of low quality chunks. That means basically measures the worst case experience, and average quality changes per chunk, and the total rebuffering. And we evaluated basically two schemes. Panda is the probe and adapt with consistent quality. These people actually consider the quality. And ours is a lot easier to implement because we are using the chunk size as a metric for quality, whereas these guys actually measure the VMAF. So doesn't exist right now in the current standards. And BOLA is the buffer occupancy-based Lyapunov algorithm. Enhanced is whether you take the peak or the average or the segment peak. And those are all described in these papers. So the Panda-CQ is a dynamic programming-based algorithm. In fact, it's worse than the MPSA. It's about 500 times slower than our PID scheme. So what we see here is the higher quality Q4 chunks. So in our case, is basically our Kava scheme is this black thing here. And what we find is that our guys are consistently better in the quality of the Q4 chunks. Percentage of the low quality chunks, you want to be on this side. So we can see that for every one of those guys, we are quite good compared to the existing schemes. Right? So this is our scheme is this one. So it's better across everything. And Kava chooses less low quality chunks for the Q1 and Q3. So overall chooses less low quality chunks. That means our quality is going to be better than existing schemes. And again, it's about 200 times faster. This is about 500 times faster than the Panda. And we actually implemented in a dash player. And you can see that our quality measured in terms of the VMAF is more than 7, 12, and 16. Anything more than about 6, people can actually see. So 6 is where you can actually see the perceptual quality differences with VMAF changes of 6 or more. And low quality chunks are going to be lower using our scheme. And the stall durations are lower, and the quality changes are also lower than existing schemes. So the existing scheme is the PIA-E. Okay, now how do we reduce the data usage? Well, right now, most ABR schemes use something called the track-based filtering. So that means that if you specify there, I want to have, say, 80% quality with this, my data plan, they basically reduce anything above 80%, they basically cut it off and then present only the ones that are within the quality level to the user. So here we are proposing the chunk-based filtering rather than the track-based. Because with VBR, the chunk is going to be different, right? So we have a quality-aware CBR filtering, and of course, this can be used with any of the existing schemes, including MPC and PIA, all sorts of things that you can actually make those things a lot better. Another thing that we did was we included as part of our PID scheme. So this is our what we call the quad, the quality-aware data efficient streaming. So again, we have our PID, we have the optimization. But here within the optimization, we take the target quality that we want, as in terms of the VMAF, and the segment size, the chunk size, and what is the quality that we want for, what is the quality that we have for the particular segment. And those all go into this optimization as this extra parameter that we have. And also we don't want to change the quality from one track to the next track. So again, using the existing formulation, we can do that. And this is the extra term that we did. If my C hat of t is a lot more than what I require, I don't want to penalize you because my bandwidth is sufficiently large. Only when my bandwidth is smaller, where this UTR-TLT is more than C hat of t, I'm going to penalize you. So by making this non-differentiable least squares objective, which I can evaluate very easily because there's only a discrete number of things, I can solve this problem quite easily. So by changing this optimization, I can actually have a data efficient streaming. So quad is actually the closest to the offline optimal in all metrics. So offline optimal, you can actually get that by enumerating in a combinatorial way or even dynamic programming. And what we find is that existing Panda and MPC can be enhanced. These are enhanced with CBF. Our quad is actually better than any of these guys. We reduce the deviation from the target quality by 12 to 15%, low quality chunks by 19 to 44%, and average quality change by almost 30%, and the number of stalls 3 to 15 times smaller. Okay, and also the data usage by about 10% or so less. So I hope that I've given you a preview of the kind of things that are there in the 3 papers. One is, if you know how to tune your PID controllers, they can actually perform better than complicated things. And it's very lightweight. Takes only like 0.2% of the computations compared to 4% or more. In fact, Panda is more like 10%. And it's very easy to deploy. And we have extended to the VBR schemes in terms of the non-myopic, differential treatments of different scenes, and also proactive things. And in fact, you can make it a lot more intelligent by actually connecting it to a GPS, for example. When you're going from point A to point B, you could actually be knowing the map of the bandwidth, approximate map over, say, the next 3 hours. You can have another outer loop controller that actually plans for those kinds of things. And it significantly outperforms any of the existing so-called schemes that came out of fairly complicated techniques. And we developed the so-called chunk-based filtering that can be applied with any of the existing schemes, and also a PID version called Quad. And we're going to now extend this to 360-degree videos and also make it adaptive and intelligent using some of the machine learning type techniques. Okay? That's what I have. Any questions? Yeah.
The way you're showing improvement in performance is showing improvement in each of the aspects, right? Each of
Right.
which have a model that takes all of them to account in a holistic fashion.
Right.
So given a video that has all of these, can I come up with a single number that encapsulates all of these aspects that I need to evaluate?
Yeah. Right. In fact, our third objective function that we had is sort of like doing that. That's right. Right. So if you go take a look at our third objective function, right? This one. So the first one is sort of like the bitrate stuff. The second is the quality with respect to the reference. And these are the quality changes from one time step to the next time step.
There are models that have been validated on subjective studies.
Yeah, I don't know much about this, but our computer science guys are saying that the VMAF is sort of like validated with the actual subjects. So that is the one that we have been using. So the key message that I want to give it is that this is one way of addressing the thing. For example, VBR, we could have addressed using, for example, the D part of the PID rather than the way that we have done. And the key message that I also want to give is that those three principles are valid, I think, in terms of the non-myopic, differential treatment of different complex videos, right? In terms of the chunk size things. And the third thing is you need to have this preview control. That's something that looks ahead, say, the next 40 seconds, next 3 minutes, next 15 minutes, and then maybe the entire travel period if you're going to be traveling in a car, right? So that hierarchical multi-scale, multi-time scale controller, I think, is the one that will actually be intelligent and adaptive. Okay, so that's basically the message that I want to get across.
How are you planning to translate this?
Yeah, fortunately, if you go and take a look at some of our collaborators, so AT&T is involved. So AT&T has the content, they own the DirecTV, and they are the ones that are going to implement this stuff. Yeah, so that's the reason why we were able to actually implement in the dash as well as collect all sorts of traces. In fact, AT&T people traveled across the United States and collected the actual traces too. So. Yeah. I think right now I think we have 3 patents maybe that are filed. Yeah. So every one of the papers, I think, that's what all these big companies do is patent things. So my role has been, hey, how do you solve the problem? And the implementation is being done by the computer science professors, a guy from Minnesota and the AT&T guys. Actually, this has been a fun project. So is it like my return on investment is, I spend maybe this much time and were able to do a lot more because other people did all the work. Right. Hopefully.